Welcome to the Explainer. So, our goal today is absolute clarity. We're taking the comprehensive CVA6 requirement specification document and, well, distilling it down into hard, actionable data. If you're part of a professional hardware engineering team and you're staring down your next SoC tapeout, you gotta know exactly what this core can do, right? You need to know its boundaries, how it performs, the whole shebang. We're gonna break all of that down for you right here, right now. Here's our roadmap for this briefing. We'll start by meeting the CVA6 processor. Then we'll get into architecting for high performance, ensuring industrial-grade safety, hitting your PPA targets, and finally, integration and design rules. It's going to be structured, highly detailed, and focused entirely on getting you to a safe, performant tape-out. Okay, let's dive into this. Section 1. Meet the CVA6 processor. At its core, pun fully intended, the CVA6 is an open-source RISC-V compatible application processor. But the absolute critical keyword to focus on here is industrial grade. Listen, this isn't just some academic experiment anymore. It actually evolved from the highly respected Ariane project out of ETH Zurich and the University of Bologna. And now it's written completely in clean system Verilog and maintained by the OpenHW group. Basically, it has matured into a core that's absolutely ready for rigorous professional implementation.
Now, obviously, it's not a one-size-fits-all kind of deal. The core actually comes in two main flavors tailored for different professional scopes. On one hand, you've got the CV32A6, which utilizes the 32-bit RV32 base configuration, and then for heavier lifting, you have the CV64A6, leveraging the 64-bit RV64 base. So whether you need a really compact, efficient 32-bit engine or a much more expansive 64-bit powerhouse, the foundation remains totally consistent and, crucially, highly verified.
But what exactly are you integrating? Look, any hardware engineer knows verification requires strict, impenetrable boundaries. You literally cannot verify what you haven't defined. So there are hard lines drawn for these IP blocks. For what's explicitly in scope, you get the core itself, the L1 write-through cache, control and status registers, plus interfaces like AXI and Open Python PMash. Just as importantly, though, we need to talk about what is explicitly out of scope. That includes interrupt modules like CLIant and PILIC, the debug module, and L1 writeback caches. By establishing these strict boundaries up front, verification teams know exactly where their responsibilities begin and end. It's how you get a bulletproof validation process.
All right, with the boundaries set, let's talk about what's happening under the hood. Section 2, Architecting for High Performance. We all know the golden rule, right? Your processor is really only as fast as your memory subsystem. You can have the absolute fastest pipeline in the world, but if you're starving for data, you are dead in the water. So how exactly does the CVS6 handle those dreaded memory bottlenecks? What's truly fascinating about the L1 write-through data cache, the L1WT, is its sheer flexibility. It is incredibly configurable. You can actually scale it from a lightweight 0 kilobytes all the way up to 32 kilobytes, totally depending on your area constraints, which honestly is a brilliant trick when you're trying to balance area against performance. It's also built for serious reliability, supporting EDC and ECC data extensions. Plus, it integrates seamlessly with the PMash line invalidate command and can be dynamically enabled or disabled via CSRs. The write-through behavior here gives you strict memory ordering guarantees, which, let's be real, is an absolute lifesaver when you're managing complex memory coherency in a multi-core SoC. Of course, performance is also heavily dictated by the instruction set architecture, and RISC-V is famous for its modularity. When we break down the ISA requirements, you have your mandatories, the base integer instructions, multiply/divide, atomics, and basic control flow. But the optional extensions are where you really get to optimize for your specific workload. Need to crunch some heavy numbers? Just drop in the optional F and D floating point extensions. Or maybe you need to reduce code size to save on precious memory. You'd bring in the C extension for compressed instructions, or maybe ZCB and ZCMP. You literally only pay for the silicon area of the features you actually need. Now, customization is fantastic, but for modern applications, a fast chip just isn't enough anymore. It has to be a safe chip. Let's pivot to Section 3, Ensuring Industrial-Grade Safety. I want you to consider this quote directly from the spec. Performance counters matter, especially in safety-critical applications. I want to pause on this because it kind of flips a really common assumption on its head. Usually, we think of performance counters just as profiling tools for software developers trying to shave off a few clock cycles, right? But in industrial hardware, they're actually a fundamental pillar of functional safety.
Let me explain why. The hardware performance monitoring unit in the CVA6
gives you absolute, deterministic visibility into the core state. It includes mandatory counters like M-cycle and M-stinchret to track time and retired instructions, but it also offers 6 optional generic 64-bit HPM counters, and these can track 22 highly specific microarchitectural events. I mean, think about the visibility that gives you. We're talking cache misses, TLB misses, pipeline bubbles. By using the MHPM event CSRs to select and monitor these specific events, your safety systems can detect anomalies, lockups, or timing deviations in real time. This is exactly how you guarantee your silicon is behaving perfectly as intended. And let's look at how this builds into actual hard security countermeasures, specifically the fence.t custom instruction. You know timing side channel attacks, like Spectre, right? They exploit the state left behind in microarchitectural structures. Well, fence.t is a predictable security tool designed to stop this cold. Step 1, the fence.t instruction is triggered in the pipeline. Step 2, it aggressively and entirely clears the L1 caches, the translation look-aside buffers, and the branch predictors. Step 3, by wiping that microarchitectural state clean, Spectre-like attacks are successfully mitigated. It's a forceful, highly reliable way to isolate secure execution environments. Safety and security are completely non-negotiable, for sure. But eventually, the math has to work out. You gotta hit those power, performance, and area constraints. So, Section 4, hitting your PPA targets. Greater than 2.1. That is the benchmark target you really need to remember here. The CVA6 targets greater than 2.1 core mark per megahertz. For an open source, highly configurable core, that is an aggressively competitive performance baseline. It genuinely proves this architecture can hold its own against proprietary blocks in serious, heavy-duty industrial applications. But how does that actually translate to real silicon? Well, it depends on your deployment. If you're prototyping or deploying on an FPGA, the 32-bit CV32A6 targets greater than 150 MHz on a standard Kintex 7. But when you move to a full ASIC fabrication, the performance scales massively. The 64-bit CV64A6 is aiming for over 900 MHz on 28-nanometer FDSOI technology. This gives you a really clear, viable path from affordable FPGA prototyping straight through to high-performance ASIC tapeouts. So, the architecture is solid, the safety is locked in, and the numbers look fantastic. How do we actually put it on a chip? Section 5, Integration and Design Rules. Integrating the core obviously requires compliance with modern interface standards. The CVA6 spec mandates an AXI5 memory bus. But crucially, this isn't just some basic connection. It requires support for atomic transactions to handle those RISC-V A extension instructions safely across the memory hierarchy. It also requires the use of user and R-user extension bits. All of this ensures robust, standard-compliant communication with the rest of your SoC. Finally, the OpenHW group enforces some incredibly strict core synthesis guidelines. Consider the required constraints: a supersynchronous design, a single clock input, absolutely no multi-cycle paths, configurable reset signals. Now, why does this matter so much? Because complex clocking and multi-cycle paths are literally the #1 cause of timing closure nightmares during synthesis. By enforcing these strict, technology-independent design rules, the CVA6 ensures predictable, reliable synthesis across entirely different foundries and technology nodes. It completely takes the guesswork out of the physical design phase. So, the crucial takeaway is this: the specification is rigorous, the performance targets are clear, and the design rules are built from the ground up for absolute reliability. Which really just leaves us with one final question for you. Are you ready to integrate an industrial-grade RISC-V core into your next SoC tapeout? If the answer is yes, or even just a maybe, your very next step should be to pull up the OpenHW Group's CVA6 user manual and see exactly how these specs align with your engineering team's next major project. Thank you so much for joining me for this explainer, and happy engineering.